Okay, so a few communication details. So basically, um, I'm uh, I'm almost finished correcting the assignments, and just to make sure that I received everything. Let me check the one that I received. So I received Giovanni Avveduto, Alessio Balsini, Alessandro Di Fava, Carmelo Di Franco, Michele Linardi, Marco Pagani, David Perillo, Gastone Rosati Papini, Stefano Varotti e Jung Xiao. And instead I didn't receive the assignment by Matteo Dell'Aglio, Alessandro Bionti, Andrea Piarulli e Francesco Lauria. Everything okay? Am I missing somebody?
No.
So I have not received the assignment by Matteo Dell'Aglio, Alessandro Biondi, Andrea Piarulli e Francesco Lauria. That's correct? All the others have sent something. Okay, so I'm almost finished, so I guess that this evening I will send out the emails with the corrections. Okay, so another thing I would like to say is regarding the. So I put right now all the slides online on Didactive, so you can download all the slides, and let me know if you find some error or something, and also all the exercises that all the examples I show during the lectures should be there. One thing about the performance issues that I've shown last time. So remember that last time we talked about parallel programming, and I've shown you an example of calculating the number of all the elements in a matrix. And I show you this code and the implementation in C++ by using a common vector result. And I told you that this is going to be slow. But the reason I gave you was maybe not the correct one. And in fact, one way to try to accelerate that code is to put a local variable called temp to see what happens. And so I ran several experiments with the two versions using a global variable, global vector result, and updating the global result value directly into the body of the threads, and using instead a local variable, updating the local variable during the thread execution, and then putting the results into temp. And what happens if I use just one thread or I use multiple threads? As you remember, my computer has 8 virtual processors, actually 4 physical cores, and every core has 2 hyperthreads. And so basically in total I have 8 virtual processors on my Dell laptop. And I did these experiments. So basically the red dots are by using the local temp variable, and the green dots is by using the global result vector. And as you can see, so there is a speed up in using the local variable, but the speed up in using the local variable is due probably to the fact that the compiler is smart and so uses something in the register, or the cache is accessed in a smart way. So even in a single thread implementation, using the local variable is much faster than using the global variable. Okay? And I think this has to do with the way the cache is implemented in hardware. So basically, when you use this kind of approach, the compiler makes some assumptions on the way the code is organized, and if the variable temp is local to the thread, it can optimize much more the code, and the cache, of course, takes advantage of these optimizations, and so it can go much faster. Instead, when you use a global variable, even when you are in a single thread, and main, of course, the compiler wants to stays much more conservative. Okay, so a lot of optimization are disabled, and in particular is going to put some barrier for sequentializing code across different threads. And so this means that not all hardware features of the cache can be used, and the code is going to be much more slower. So this explains the huge difference in execution between a single thread and local variable, and single thread and global variable. As the number of threads increases, the speed up obtained by the global variable stays pretty much constant. And again, this is probably due to the fact that the cache is implemented in a smart way. So there must be at hardware level. Unfortunately, I did not have the time to go deeper into the analysis, but probably at the hardware level there is a very intelligent and fast way of accessing the cache, which works very well for a single thread. It works also quite well also for multiple threads, but you don't gain too much in doing this. So at the end, you don't have too much speed up. And the same difference holds for the global variable. So you have some speed up, but not too much after a certain number of threads is used. Okay, so the lesson to be learned by this graph is that it's not easy at all to forecast, to understand what's going on at the hardware level, because of the many layers of optimization that are used at the hardware and at the compiler level. So it's not very easy to understand how to speed up code like this by using parallelism. Now, this is a very extreme case. Basically, the computation is very simple. It's just increasing a variable and going through many elements. So it's a very specific case, and probably when you have multiple threads in which the local computation is substantial, then the amount of speed up you are going to observe is much more. But the message to pass here, the lesson to be learned, is that it is not easy at all to parallelize code. And every time you have to be very careful in what happens at the hardware level, what happens at the compiler level, and how your code is organized at in the number of variables, which variables are global, the amount of synchronization you have, and so on and so forth. And also maybe the amount of the performance figures you are going to obtain on a different platform would be completely different. So it's not easy to write portable and optimized parallel code across different platforms. Okay, this is just to conclude the example on parallel programming and performance. Okay, today instead we are going to start the last part of our course, in which I'm going to talk a little bit about design, and in particular a little bit of software engineering.
Sorry, excuse me.
Yes.
Not the slide. Don't see the.
You don't see the slides? So you didn't see the previous graph then?
No.
Should have told me before. Okay, so I'm going to show the graph now. Maybe it makes much more sense what I said. So the green dots are global variable. So this one. Okay? So increasing the global result variable, and result stays in a thread. Sorry. So you have a vector of integers, and every thread increase is on variable. Okay? And this instead is local. You're going to use a temporary local variable, which you increase across the double for cycle, and then you put the temp into result at the very end. Okay, so two alternative implementation: global and local. Okay, and this is the result of running several times the program, and every time measuring the execution time, the total execution time needed for completing everything. So on the x-axis you have the number of threads, on the y-axis you have the number of microseconds. I made with respect to the previous lecture, I made the matrix much smaller. So basically, I don't have the problems like, oh, it's not going to fit too much into the cache. So I try to minimize some of the strange effects due to cache. And so what happens? It happens that with a single thread, or only one thread, using the local variable is much more convenient. So you go from 130,000 microseconds, or 130 milliseconds, down to 20 milliseconds. Okay, so this is 6 times less. And just single thread, just by changing and putting temp local. So what happens is probably the fact that the compiler is going to optimize this double for cycles a lot, due to the fact that this is a temporary variable and it's local. So the fact that it's local helps in using a lot of optimizations in this double for cycles. Instead, here, many optimization cannot be done because the result is global and it's shared between this body and the main. And so increasing the result has to be done in the proper way, even when there is no synchronization. For example, some sequentialization points must be respected, because every thread must be able to see the effect of this increase, okay, in the proper way. So many optimization here cannot be done, and instead this optimization can be done here. So this gives you a speed up of 6 times. If you increase the number of threads, the speed up by using local variables is there until more or less 3 or 4 threads, and then disappears. And this is probably due to the fact that my PC has 4 physical cores, but only and so basically, even if you can run 8 threads in parallel, it's using hyperthreading. Hyperthreading means that every core, every physical core, can run 2 threads in parallel, but these threads are going to share some of the hardware physical resources inside the core. For example, the arithmetic logic unit is going to be shared, and so it cannot be used in parallel. So this means that you can achieve a speed up until 4, but not much more than that. And instead, by using global variable, you still have a speed up, and this is due to the fact that probably the cache is implemented in the proper way. And so also, even if the variable is global, allows you to have some speed up. But again, the major speed up is due to the compiler doing nice optimization on the increase of variable temp instead of increasing variable result. Okay? Do you have questions on that?
Okay.
Okay. So if you, as I said before, the lesson to be learned is that it's very difficult to optimize this kind of code. It's very, very difficult because it depends on many different things. It depends on the hardware. So it's difficult to write a portable code that is optimized on all platforms. It's going to depend on the way you organize the code. It's going to depend on the amount of independent computation you have to do. Here is very small, but in general it can be quite larger. And so it's not easy to achieve a substantial speed up by using multi-threading. Okay, so now we start with agile programming. So here we are going today I'm going to present some of the recent development in software engineering and programming in large scale. So first of all, something about unit testing. So you already know, because you used the unit testing in the assignments. So you should already know probably what does it mean to do unit testing. So let's review a little bit that, and let's see how companies are using unit testing in a massive way. So as you may know, testing can never be exhaustive because you can never really discover all the program bugs by running tests. And this is due to the fact that test coverage cannot be exhaustive. The number of tests to be executed to check everything is badly exponential. Okay? So the goal of doing tests is not to discover all possible bugs, and is not, of course, to demonstrate correctness of your code. Running tests is useful just because you can catch more easily some bugs. The most easily evident and probably also the most important bugs in a program. So you are never going to discover all the bugs. You have to be careful about that. But you can discover some bugs. Also, testing is useful because it gives you some evidence that the program is conforming with the specification. So you have a specification. The customer gives you what he wants, a list of things the program should do, and you write tests to show yourself and to show to the customer that the program is doing what he asks the program to do. So it's a little bit more than demo, because demo is just marketing. And it's not verification, because verification is formal methods that prove mathematically that your program is correct. It's something in the middle. It shows a little bit more formally than just a demo, and a little bit less formal than a verification. But it shows that the specification has been respected by the software you wrote. Okay, so it's evidence. So even if testing does not prove correctness, it proves something, and something is always better than nothing. So it's a very practical thing if you want. And if you want, every programmer knows and acknowledges that testing is an important activity in coding. So you learn at school, at university, that programs should be tested and programmers should write tests. Now, tests means a lot of different things. You have unit testing, functional testing, integration testing, and so on and so forth. Okay. Here we are going to discuss unit tests, which is a specific aspects of testing. Okay. The unit test can be considered a tool for the programmer, not for the customer, but for the programmer. So it's something for you as a programmer to write better programs. So unit testing is a method by which individual units of source code are tested just to see if they are good. So a unit is the smallest testable part of an application, typically a class or a function or something that has a certain unity, so something that stays together well, but of course that can be tested alone. So it's something that you can put apart from the rest of the program, consider that as something that has a certain unity, a certain consistency, and that you can test in isolation. So the idea is to test a unit, so a small piece of code, in isolation from the rest of the program. What are the goals? What are the objectives of unit testing? The objective is to find bugs in code, of course. Then one very important that we will see in a little while is to be able to refactor, so to modify, to change the code later and check that everything continues to work. And finally, to check that modification to other units on which the unit under test depends upon will not break the assumptions and invalidate the behavior of the unit. Okay? So item 2 and 3 are very important because they are also called regression testing. And they are fundamental to check that some properties hold. For example, we have seen sometimes during pattern, when we started to talk about patterns, we have seen the Liskov substitution principle that says that basically a function should depend on a function that uses a pointer or a reference to a base class should not depend on the fact that the pointer is pointing to a specific object of a derived class, but should only depend on the base class. So if you substitute the object of the base class with an object of the derived class, everything continues to work. And that's exactly what we can test with unit testing. So we write the test and we pass the test to the base object and the test works. And then later on we write a derived class and we run again the test by passing an object to the derived class and the test should continue to work. And every time we add one additional derived class, the test should continue to work. Okay, so we check that the Liskov substitution principle continues to work. Now, so everybody understands that testing is important because it allows us to find bugs, allows us to show that something is working, and allows us to do regression. The problem is that programmers don't like to write tests because writing tests is quite boring. It works against human nature. Right? So usually when you write code, the assumption, the programmer does the optimistic assumption that his code is correct. And then it writes a small main just to see if it works, and if it works, it continues to add new code and so on and so forth. So the programmers' minds are always optimistic. They are self-confident. They think they are writing always correct code, and so they don't want to lose time working on tests. The second reason is that it's a lot of additional code. So for small classes, okay, you write a simple function and that's it. But for big classes, it's a lot of work because you have to set up the environment, all the necessary objects that are around. You have to write very often a mock-up, that's it. If you want to test a class in isolation, and this class depends on other classes, you have to write mock-ups for the other classes. So fake classes that simulate the behavior of real code. So it's a lot of code. So you have to write the testing code, run the test, check the result, adjust everything, blah, 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 blah. The third reason is that the test code is code. And so it may contain bugs and needs to be maintained. And sometimes you do modification to the code, and this modification implies modification in the test code. So you have to maintain a test constantly in sync with the business code. Okay. So as you can see, test is a lot of work, and most of this work is not very fun because it's not finding nice algorithms. It's not inventing the new special, very fast algorithm that will solve all your problems. It's work that is boring because it's just checking that everything works. So not very intelligent. Normally, a programmer wants to write useful application code because it's a more inventive and rewarding activity and doesn't want to spend his time writing tests. So if you look at some of the statistics about writing code in industry, testing is more than 50% of the cost of development. Much more than 50% of development. It's testing. So that means that it's not some additional activity that you do at the very end when just to see that if something works or not. It's something that takes a lot of time and takes a lot of effort. So as a consequence, most programmers simply do not test. Another reason for not testing is that there is never enough time. Most of the people in software industry are pressed by deadlines because companies are running always for finishing the code in time before the deadline for several reasons. We will analyze all these reasons in the next slides, but in general, programmers are always pressed by deadlines, always, all the time. And so, if the deadline is approaching fast, you don't want to lose time in testing because you have to finish coding, and so you cannot waste time testing. Okay, so the programmer concentrates on meeting the deadline, so it concentrates on important things and just doesn't test. Also, tests are code. We may introduce bugs in testing code, so producing false positives, and this is a lot of time that gets wasted, and so many other excuses. So most companies will just say, okay, we have to do that in a systematic way. So they follow the hardware approach. So in hardware, usually there is a section, a team in the company that is doing design, and a completely separate team that is doing testing. And the idea is that the people in the testing department should not know anything about the design, so they can produce the test independently. And many companies in software use it to do that. So you have your development team, which just develops and has a lot of fun, and then you have the testing department, which are the people, the unlucky people that spend all their time just testing. So companies try to force programmers to write tests. And since it's against human nature, after a while the programmer don't like that. So they don't put too much emphasis, they don't put too much intelligence in doing the testing. So can we make testing a little bit more attractive? So the idea is to use automatic testing as much as we can. This doesn't solve all the problems, of course, but makes the testing activity a little bit better. So the first thing is the programmer should not spend time in checking the output of the test to see if everything is okay. So using, for example, a library like Catch that you have used in the second assignment, it's very convenient because you embed the checking in the test itself. And so the only thing the programmer wants to see when he runs the test is okay or fail. Doesn't want to see endless screens of text output that he has to check manually. Then you have to make it easy to run suites of tests. And all tests should be grouped in test suites so that you compile and execute them with one single command. And again, this is what the library I recommend you does. You just can run the test with a simple command, and passing command line arguments, you can select also one subset of tests. And as soon as a new test is written, it is added to the test suite and executed along with the other tests. Tests should be written by the programmer before coding the unit. So this is called sometimes test-driven development. So when you need to write a new class or a new unit or a new function, the idea is that you start by writing the test, and of course at the beginning the test is not working. And the test basically gives you also a way of using that class. So suppose you are writing a class, and the class has like 3 functions in its interface, and you have not implemented these functions yet. You just have the interface of the class. Now you write the test. Writing the test is like wearing the customer hat. So sometime back at the beginning of the course, I told you that when designing software, the programmer should wear 2 different hats. He should consider himself as the implementer of the class, of course, but he should also consider himself as the user of the class. And he has to wear both hats one at a time, of course. So at the same time, he has to be the user, so he can design a nice interface, and he has to be the implementer, so he can implement the class in the right way. Okay? So writing tests before coding the class helps you in doing this, because you start by writing the class interface in the HPP file. Then you write the tests for that class. When writing the test for that class, you are basically writing patterns of usage of that class. So you are forced to use the interface of the class in the test. Now, you write the test, you compile, you run the test. The test fails because the functions are not implemented yet. Then you start implementing that interface. So you wear the implementer hat, and you continue to implement and compile and run the test until the test works. When the test works, it means that the interface you have thought about the class is complete and has been implemented correctly. Okay? So you start by writing the interface of the class. Then you write the test for that class. And of course, the test doesn't work at the very beginning. Finally, you implement the class, and every time you compile, you also run the test. And when you have finished it, it means that all tests compile and run correctly. And this is exactly what does it mean, run tests often. Run tests often means run tests every time you compile. So the habit of running tests should be automatically embedded in the development tool. So right now what happens is that when you write code, you compile to see if at least it compiles. And then you continue implementing every time compiling. So in addition to this, now the objective is every time I write something, I compile and test. And only when all tests have run correctly, I can say, okay, I'm done, I'm finished. So what are the advantages of this method? So it's better because you substitute debugging with testing. So testing is done while coding. Debugging is done later. So testing is like coding. It's just coding. It's a special kind of coding because you are not coding real things that are going to execute in your program. You are coding software for checking other software. Okay? But still, it's coding. So it's much better than debugging because debugging means, okay, going with the debugger or with the inserting prints into your code just to see where the error is. And very often, debugging is done after you find the bug in the production code. So you are running your code, the code crashes or does an incorrect result, and so you have to go very painfully through all your code following the thread of execution until you find the error. And usually debugging is done at the very, very end when you find it. And so it's a very an activity under pressure because you need to solve the bug, right? Testing instead is done while you are coding, so you are less pressed. You don't need to, you have not the pressure to find the bug, otherwise something very bad is going to happen to your company. Finally, tests are there to stay. So tests you write and you can run many, many times. While debugging is just you going through the code, and so it's a lot of waste time. So if you compare debugging and testing, testing is much superior to debugging, right? So, and in particular, testing may be more funny than debugging. A lot more fun than debugging, actually. So if you think about that, maybe the programmer can be convinced that it's much better to test than to to debug. Finally, testing is a fundamental tool to address the need for change. What is it, the need for change? The need for change is that usually the programmer ignores the fact that your software is continuously going to change. Continuously. So we will go back and analyze in more details what it is this need for change. But for the moment, just trust me if I tell you that when you start a new project in a company, the probability that your code you are writing at the very beginning does not exist anymore at the end is very, very, very high. So you need to change existing code or add additional code functionality. If you need to do that, and you need to do that, you want to make sure that existing tests do not break when you do some change. And the interface is consistent across all versions of your program. So you need to do that, and to do that you need regression testing. Okay. In particular, you want to make sure that if a test doesn't work, maybe you introduced a bug in the code that breaks existing code. Or maybe you violated some assumption that was not very clear in the specification, but has been captured some way by your tests. For example, again, the Lisco substitution principle. Or maybe you need to change the test. Maybe it's the test that is wrong because the specification has changed and the test is not valid anymore. But in any case, since you test every time you compile, you can immediately spot the error and immediately change what you need to change. This is the alternative. What is it, the alternative? The alternative is to discover the bug during the integration testing, so at the very end, where you need to trace back the problem and debug your code to find where the problem is. Okay, so if you compare again debugging when you find a bug or testing in advance, the first alternative at the end is better because it's less time consuming. Of course, you can never do a complete testing coverage in the unit test because it's too time consuming. So how much test should I write for your class? That's a difficult question. It's actually, you can only learn how much test you need by actually writing on a real project and writing tests every day. After a while, you get the confidence to understand which tests are really needed and which are not needed because are superfluous. Huh? So, in general, you don't need to write too many tests. You need to write a few meaningful tests. So, one meaningful test, for example, is the normal functioning of your interface. So, the typical use case. As I said, writing a test is a little bit like writing an executable specification. How to use your code. And if you want, it's a little bit like writing documentation, because very often when you read the test, you understand how to use that class. So, the first test you should write is the typical use cases for your class. For example, suppose you have your shape class, like in the assignments. What you want to do is, the typical use case is how to create a specific shape class, how to move, rotate the specific class, how to put the class into a group, and things like that. So these are the typical use case. The other test you should write is checking boundary conditions, because the boundary conditions are the source of most errors. In particular, programmers always concentrate on the typical cases. It's the thing, when they write an algorithm, they have in mind one specific use case. The problem is that the user often uses your class in a very strange ways. And so you have a lot of boundary conditions to check. So the idea is to write tests for checking boundary conditions. For example, what if the function needs a file and the file does not exist? Does my code crashes with a segmentation fault, or maybe it just throws an exception or returns an error? Or what if I try to extract from an empty container? What if I try to delete a shape that is not there? What if I try to delete something from an empty group? And things like that. So, You have to check the typical use cases, but you also have to check the boundary condition. Okay? Or what if I have to run a sorting algorithm on an empty vector? Does my function takes into account the fact that I can have an empty vector? So this is what you really need. A few meaningful tests, typical use cases, and boundary conditions. Of course, as I said, testing coverage, 100% testing coverage is impossible. So there is no limit to the number of tests you can write. But after a while, with a little bit of experience, everyday experience, you will start understanding which tests are useful and which are not useful. Of course, testing can never completely substitute debugging. As I said, you cannot have 100% coverage. So at some point, you will discover a bug which was not covered by your test cases. Well, then you need to debug, of course. But one nice thing you can do is that when you discover the bug, you can immediately add an unit test to check the error will never occur again in the future modification. So typically what you do is you discover the bug. Before actually solving the bug, you have to think a test that can highlight that the bug exists. Suppose you understand that a function has a bug when you pass this, that, and that parameter. When you pass, for example, an empty string, and then if you pass an empty string to a function, the function doesn't work. Okay, so then you write a test in which you call the function with an empty string and you highlight the error. Then you compile, run, you see that the test fails. Very good. Now you solve the bug and you compile, run again, and you see that the test now works okay. Perfect. From now on, you have a test to check that this will never occur again in the future, because sometimes bugs reappear magically after a little bit of time. I don't know. You solve a bug and after 1 month you find that the program still behaves incorrectly and you think, hey, I solved that bug, but for some reason, anything can happen, the bug is still there. So by writing immediately the test for that specific bug, you can actually highlight and keep track of the fact that in the past there was a bug and has been solved. So as I said, when you write tests, you concentrate on the interface. So while writing tests, you wear the client hat, the customer hat. While writing code, you wear the implementer hat. So writing tests is similar to writing a specification for the code. And the test is useful also as documentation, because if you want to know how to use a function, sometimes you can look at the test and understand how the programmer that implements that class thought about using the class. So the typical use case is there. Finally, the great advantage is that you have a clear point on which you can say, hey, I'm done, I'm finished. That point is when all tests work. So when every test is working, it means that the interface is working, the implementation is working, and so you have done with that specific class. Of course, there is always space for improvement in the future, but for the moment, you have done implementing the class. So you have a very clear point that says, okay, I'm done. So all these ideas have been put together into one methodology, which is called test-driven development. And this methodology has been one of the main points of the extreme programming methodology proposed by Kent Beck. So this researcher, Kent Beck, proposed many years ago extreme programming as a way to revolutionize the way of writing code in software industry. So what is test-driven development? As I said, you start by writing the test for your code. Then you check if the test fails. If the test succeeds, you rewrite a new test until you think that you have enough. If the test fails, of course, what you have to do is to write production code. So the implementation of your class. So at the very beginning, you start writing the test for your class. The class is not there, so the test is going to fail. Then you write production code. You start implementing. And you continue implementing and run the test, implementing and run the test while the test fails. When all tests succeed, you clean up the code and you repeat. You start writing new tests for new pieces of software, and then you, of course, compile, check if tests fail, and continue like that. So it's a cycle in which you start with a test, and after that you write production code. Now, there has been a lot of criticism about test-driven development. And so you will find around a lot of research on software engineering literature about test-driven development, how effective it is, what if a company changes from a normal waterfall model to agile development, things like that. So there is a lot of literature in that. What I can say is that a lot of companies, software companies, have moved to this kind of development recently. And in particular, there are tools that help companies implement this kind of methodology. And these tools go under the name of continuous integration tools. So what is a continuous integration tool? So it's an integrated environment, distributed usually. And the idea is that you have to, so basically there is a repository, a central repository where the code, the source code is stored. And you have a cycle for implementing the code, which is you start writing the test and the code, of course. And if you want to commit, before committing your code, an automatic compilation and testing cycle starts, and only if all tests run and succeed, the commit in the source repository can actually be done. So basically the idea is that you are going to have one integration step at every single commit. So I don't know if you have ever tried to work with Git or SVN or one of these source versioning tools. Well, continuous integration, they of course are based on this source integration, source versioning tool, but they had the fact that automatically every time you have to compile and test. And usually this is done by using a cluster of computers, so that every programmer can commit independently, and you have many PCs that can run tests and compilation in parallel. Okay, so it's something a little bit more substantial than just a simple compilation and commit. So let me see if I can show you something. So you can look at the site of this researcher, Martin Fowler, which is one of the authors of a book that is called Refactoring. And we are going to talk about refactoring in the last part of this set of lectures. And this is one of the fathers of agile programming, and explains here what is continuous integration. So basically, invite you to go and go a little bit deeper on what I say by looking at this website where Martin Floer explains you what is continuous integration. And the continuous integration software, you can find a list here on Wikipedia, for example, if I remember well. And there is something from Apache, and some is of course open source, but it's not very easy to configure, and something is provided by companies. So big companies, everybody has his own way of doing continuous integration, Microsoft, IBM, of course, and then there are independent companies. For example, Atlassian is the one that provides you also with the Bitbucket free repository, Git repository, and it provides also, it's a company, so it also provides commercial tools, and one of these is Bamboo, which is based on Eclipse. So Bamboo is a continuous integration tool based on Eclipse. Okay. And now it's not very easy to use this continuous integration tool because basically you have to change a little bit also the mentality of the company and the programmers. So what you have to do is to go and instruct your programmers to enforce your programmer to use that. And so it's not very easy. It requires a certain rigorous and structured approach to impose this practice to our programmers. Okay, so if you agree, I will continue and finish a little bit earlier today. So we skip the break and we continue. And so we are going to talk a little bit on agile programming. And so what is agile programming? So one aspect of agile programming is test-driven development, but it's actually much more than that. So agile programming means basically making the development process much more agile, so flexible, so not rigidly structured, but more flexible. What is the philosophy? So we are going first to discuss a little bit the philosophy and why agile programming has gained so much popularity in the software community. So first of all, we have to understand how software development works. And so to do that, you have to try to put yourself in the pants of a manager. So suppose you have a manager and you are asked to organize a team of programmers for achieving a certain software project. So you go to the client, you have to, it gives you some specification, and you have to realize a software project. And of course you are a manager, so you don't realize the software project, but you can organize the team and you can contract with the customer. So let's look at the process of developing the software and let's see what the manager can do about that. So what are the variables that a manager can control in software development? So you can consider that as a software development game. There are external forces, customers, other managers, okay, which can pick the value of 3 out of 4 variables. So you have cost, time, quality, and scope. These are the 4 variables. And the manager can pick and fix the value of 3 of them, and the 4th is going to be dependent on the other 3. Of course, the final objective is to have the software development process to be successful, and of course you want to minimize the cost and maximize the quality, of course. Now, some managers they think they can control all of the 4 variables. So they think they can achieve a certain objective with very little money, in very little time, with very high quality and very large scope. Of course, that's not possible. Cost. What is cost? Cost in software goes to salaries of programmers. So it's the amount of time multiplied the amount of programmers, basically. Okay? So cost is related to time and is related to the size of your team. How can you control cost? Of course, cost also depends on how much cost to the final customer. So the manager wants to stay very low, because the lower the cost, the more money he can make, and or the smaller is the final price to the customer. So he has a competitive advantage. Okay. So how much money do we have to put on a project? So if you look at a Kent Beck book, what Kent is telling us is that if you already have assigned a certain budget to a project and you want to speed it up, putting a little bit more money can help, but putting since the beginning too much money too soon creates more problem than it solves. If you put instead too little money, the project will fail for sure. So the constraints on cost are that if you don't put enough money for finishing the project, of course you're going to fail. But if you, on the other side, if you put too much money since the very beginning, chances are that the project is going to fail anyway. And we will explain that in the next slides. So too much money too soon is not good. Too little money, of course, is not good. Time. More time to deliver, of course, can improve the quality and increase the scope. So increase the scope means you can implement more features, and so give a richer software to your customer with more features. So if you have more time, of course, you can work more relaxed, you can improve the quality, and you can implement more. But too much time will hurt, because if you have, I don't know, 3 years for developing a very large amount of software, and the only checkpoint is at the end of the 3 years, in the middle you don't have any feedback from a real product in the market. And so what happens is that you don't understand very well what you have to do, what you don't have to do, and at the very end you risk in developing the wrong type of software. So again, too little time, of course, is not good. More time, it's better. Too much time is not good. Quality is very difficult to control, because the quality depends very much on factors that the manager cannot really control. Sometimes the manager can say, okay, don't spend too much time on the quality of the software, because we need to do that very, very, very fast. Okay, so the programmer starts writing very bad amount of code so they can go faster, but then of course at the end you get into larger problems, because low quality software is difficult to maintain. And finally, scope. Scope means the amount of feature you are going to deliver. Less scope, of course, means you are going to do less. More scope, it means you are going to do more. Less scope makes it possible to deliver better quality, developer sooner and or cheaper, because you are going to do less. But of course you do less. The relationship between these variables is not easy at all. Suppose you are in the middle of a project and you understand you are late and you want to accelerate. So the manager say, we need to accelerate. I'm going to spend more money on that. For example, I'm going to hire 10 more programmers to help the existing programmers to go faster. Well, this doesn't work. More often than not, hiring more programmers can hurt because what you need is more coordination. More programmers, more coordination. Also, the new ones, they don't know anything about the project, so they need to learn. They need to learn what to do. They need to understand what has been done until now. They have to be included into the development process, and so on and so forth. So, putting more programmers on a team in the middle of a project sometimes makes the project fail completely. So, it would seem that that spending more would help developing faster and better, but that's not always the case. In fact, Kent says that cost is the most constrained variable. The investment has to start small and grow over time. So you have to start with a small group, develop something, and then slowly increase the team and increase the amount of time you are going to spend. These constraints on cost make the manager crazy because you have to understand how the manager works in a company. In fact, most managers, they work on an annual budget. So basically they go on to this company meeting and they are assigned a certain budget for that year. So in 2014, you have to spend so much time. Okay, now managers drive everything from cost, and cost has to do with prestige. So the higher the cost of the project, the bigger is the manager. So, and finally, the manager has to spend everything it asked for. So if the manager asked for 1 million euro, at the end of the year, he needs to spend 1 million euro. Otherwise, next year, he will get less. So if for some reason the manager asked for 1 million euro, at the end of the year he spends the half a million, next year he will get only half a million. And as I said, more cost, more important is the manager. So the manager tend to spend everything it is given, okay, by nature. That's the nature of the manager. And so the manager go crazy on costs because they base everything they have on cost. The manager actually manage money, right? Not only people, but just money. And so they drive everything from cost. So when you go to work in a company, remember this. The cost and the money that goes around the project are very, very important variable in software development. Time is often an external variable. The manager cannot control time because time is given by the customer. I want this into before 2 months. Or we are already very late. We needed this last month. Or sometimes it's driven by external variables. Even if you don't work for a specific customer, but you work for your own product and you put on the market, well, there is market pressure. You want to go there before the other companies. So time is basically uncontrollable. Okay? And finally, quality is a very strange variable because often by insisting on quality for the beginning, you get more project in a smaller time. So at the end, these three variables, cost, time, and quality, are not really easy to control. As I said, cost is not something that are really to do with the cost of the project, but very often it has to do with political things inside the company. Time is something you cannot control. It depends on external variables, market pressure and customer. Quality is very strange, and it depends on the quality of your team, quality of your programmers, of course, and often it depends on the other two, time and cost. The only thing you can really control more easily is scope. Scope means the amount of feature you are going to develop in one cycle of development. Less scope means less time to deliver something that has a meaningful, less cost, more control on timing, opportunity to achieve an higher quality. So we are going to reason on these four variables in the following slides. But before that, let's reason on the changes in software, and in particular the cost of change. So I start with a very famous old saying among engineers that says that if it works, don't fix it. And this is a very well known and respected by everybody. So if your program works, I don't touch it anymore because it's working. And it's strictly related to Murphy's law. Anything that can go wrong will go wrong. So if it works, you don't touch it. And this makes people scared about changing existing things. And it's also related to what is called the fear of change and the rising cost of change. So the basic mindset of most people in our software development market is that if it works, it should not be fixed. A typical software development is the waterfall. And this is a very old way of structuring software design. The idea is you start from specification. Then you are going to write the overall design of your software. And then after design, you go and divide your design into modules. Then you give these modules to separate teams that are going to develop everything. Then every team does its own unit test. Then everything is put together into the integration, and there is a big integration testing. Then there is verification and testing against the specification. And finally, you are ready and you can ship your code. And during the product lifetime, you have maintenance. You find a bug, you go back, you solve the bug, and you ship a patch or you ship a modification. Okay? So this seems very typical. In fact, software engineering started like that because it was basically copied by other engineering fields. So mechanical engineers works like that. You start from the requirements, then you do the project, then you realize the pieces, then you put everything together, you test everything works, you're done. So this is one single linear process that goes from the start, requirements, and progress steadily towards the end where you ship your product. And so the idea is that software engineering is engineering, so it should be like other engineering. So you do the same. You go with a linear process, you divide the process into steps, and every step comes after the other, and you never go back. In embedded system, because this is you will work in embedded system, you will find a lot the graphs like that. This is called the V model. So this is an evolved version of the waterfall model, but it's still basically waterfall model, in which there is a lot of emphasis in integration, testing, and verification. So again, you start from a requirement analysis, then you do system design, architecture design, module design. Finally, at the very bottom of your V, use code, and then you go up on the other branch by doing unit testing, which has to do with module design. Then you do integration testing. Then you do system testing. And finally, you do acceptance testing. And the flow goes from top left down and then up to top right. And that's it. So a set of steps, one after the other, from design to final product shipping. In the previous models, a lot of emphasis is put on early phases of development, in particular requirements, specification, and design. So the idea is that you complete the design before going to coding. And you fix and you close the design before starting coding. So the design has to be right. You cannot be wrong because you cannot go back. So a lot of emphasis on requirements. Requirements is that. A lot of emphasis on specification. Be very specific on everything. So a lot of people thinking very hard on what has to be done. And a lot of emphasis on design. Because if you do it wrong, then you are going into trouble later on. Since you cannot go back, you have to be very careful in requirements, specification, and design. Requirements, what the client desires. So requirement analysis is the critical for the success of software projects, because you have to be very careful in what the customer says before you actually put that on paper. So it's a very important document. Specification is just the requirements, but more formal and detailed version, often for internal use. And they also used to contain technical details, to estimate efforts, specify input-output of the different functions and so on. And this can be used to derive tests, generally. And in safety critical software, this phase is essential, is very important, critical for the success of software. So requirement is critical because it's what the customer wants. Specification is critical because you are going to write tests out of the specification. So very, very important. Design, you have to break up the project into subsystem, the interaction, and so on. And this is, again, very, very important, since a wrong design can compromise the final product functionality, the performance, and everything. So a lot of emphasis on requirements, specification, and design. So as you can see, everything is critical, very important, fundamental. Otherwise, everything is going to be wrong afterwards. The problem is that all of these critical steps are done without feedback from the programmer and without feedback from the customer. And without feedback, everything must be known and precisely specified since the beginning. And since everybody only looks forward to the next phase, any error requires changing a lot of things. In particular, an error into the design is critical because the implementation is going to be a mess afterwards. So if during implementation you discover an error in the design, you may have wasted a lot of time in coding because you have to start from scratch with a new design. Also, design depends a lot on requirements and specification. So if some specification is wrong, design is going to be wrong as well. Okay? And so everything must be very well specified and very critically precise since the beginning. And of course, in practice, this is not how it works. Because except for nuclear plant software and except for aerospace, everywhere else, requirements are always imprecise, very often volatile, and sometimes in conflict with them. So when you go to speak with the customer, of course the customer wants everything, but doesn't really know exactly and precisely what he wants. Specifications often are incomplete, not precise, or even not existing. Many companies just skip the specification phase and just rely on requirements. And these requirements are documents in natural language, in English or in Italian, and they are quite imprecise. Errors do happen in the early phase of design. We have to acknowledge that human people are subject to errors, and so you may make an error. And so very often you need to patch the design, the code, and the test quite often. And this has to do to the fact that errors are normal in human nature, and customer very often they don't know exactly what they want, and they change their mind very often. So if you look at the waterfall model, what happens is that if you put the time on the x-axis, so with different phases of development, and you put the cost of changing something on the y-axis, what you see is that as you go ahead across the different phases of development, the cost of changes increase. For example, changing something during the requirement phase has basically a cost more or less equal to zero. You just change a Word document, probably. You change a text document. That's it. If something happens during analysis and design, you are still okay because you can easily change the design. You can easily change the specification. You can redo the analysis quite easily because you are still in the early stage. Nothing has been implemented yet. If you find something wrong or something has to change during coding, the cost is a little bit higher because sometimes you have to go back and redo the design. So you are wasting time. If you find a substantial error during testing, or the customer wants something in a completely different way during testing, well, that's a lot of money because you have to go back sometimes to the project, to the design phase, and redo a lot of implementation. So that is where changes hits you more in a more difficult way. And of course, changing when you are in production is really, really costly. Therefore, due to the fact that you have these, due to the fact that everything is critical, nobody wants to change anything. So there is a fear of to change anything, and especially if it works. If it works, adding something or changing the way this is done, nobody wants to do it. As I said, if it works, don't fix it. At the same time, changes happens naturally because maybe the hardware was not adequate. I was choosing one board and the processor is not fast enough, so I need a bigger one. Or the design is not flexible. I cannot change much. Or new requirement is suddenly not. Or some module will not be ready on time, so I need to drop something, and so on and so forth. So on one side you have this curve which prevents you from changing things because it's going to cost a lot. Then you have the fear to change anything, especially if it works. And this on one side. On the other side, you have that in practice, requirements are going to change very often. And things are going to change very naturally. So what this means is that the development process, this development process, does not cover adequately the need of software development. It's wrong because it doesn't address change, which is a very natural thing in software development. So a lot of stress of programmers just because the way of organizing the work does not fit with the characteristic of this work. One of the characteristics of this work is that software changes continuously. and the development process does not address this adequately, and so a lot of stress. Also, changing something in the design is difficult, expensive, and highly feared when we are in the coding stage, because changing the design while we are coding, of course, is very difficult. So therefore, problems in requirements, specification, and designs are solved by modification in the code. So if you have a problem at the very beginning because a requirement was not really understood, so was understood in the wrong way, once we understand that the requirement has to change during coding, well, we do some patch, we do some hacks, we change a little bit something here and there. Maybe we introduce some very dirty tricks just to comply with the requirement. Now, since changes like that are very natural, patches start to accumulate. And so, little by little, your design that at the end seemed very clean, very structured, very elegant, start to become a monster just because you continuously patch your software. So what started as a clean design ends up as unclean and messy code. So when you go into a company and look at very, very bad low-level code, sometimes it's just because it's not only the programmer fault, it's just because things were changing, and so a lot of patches has to be added just to comply with these changes. Every programmer can tell that there is a difference between clean and dirty code, and can see such difference when he sees it. And dirty code causes stress because it's difficult to go back, it's difficult to maintain, it's difficult to extend. So in a perfect world, we will always have to deal with clean code. So the dream is to achieve this curve. This curve means the cost of change remains constant across the software development life cycle. Of course, this is a dream, and it's basically impossible. What is a little bit more adequate is probably something that stays in the middle. The cost is very little at the beginning, and it starts increasing, but slowly, as we go ahead during the development. So we are going to talk about that in the refactoring part, and also another set of slides I'm going to give you later on is the Scrum methodology for organizing development teams. Okay, so tomorrow we will talk about refactoring, and then Friday I think we are going to talk about the Scrum methodology. Okay, so as promised, we finish a little bit before because we didn't have the break. Do you have questions on that? No questions?
Okay.
Okay, so I will see you tomorrow then, 3:30. Bye bye.
Bye.
Bye.